Okay, let's pick up here with video 3.3, NMR spectroscopy. Again, thinking about electromagnetic radiation and how we interrogate atoms in biological molecules. And I'm sure we've all had some experience with NMR before, but again, what I'm trying to do here is to pull back the curtain a little bit on how we use these techniques to solve the structures of biological molecules, often much more complicated than the small molecules that we study in organic chemistry by NMR. So there's a lot of information on this slide, and let me just break it down for you. Every atom has a quantum characteristic known as its nuclear spin. Now, it's not a spinning top, but it's easy to visualize it as a spinning top with that spinning with some frequency. And when we hit that spinning top with radiation that happens to be in the appropriate wavelength range, right, the spins resonate. And it's that resonation, that ringing of the spin, that gives us our NMR signal. Now again, that's a little bit of well, it's very much of a simplification of what's actually happening, but it's easy for us to think about that, and it's actually common to think about the spins in a sort of a classical way as something that's precessing around an axis. Again, that precession is what is sensitive to radio frequency, millimeter wavelength range electromagnetic radiation. The trick, however, is to create a homogeneous magnetic field, which we'll often denote with this B naught. And what I've done here, you can imagine that this is actually a circular or a toroidal magnet. And what I've done is just take a slice through it. And you can see that what we have really in the magnet is just a coil of wire, and it happens to be this niobium tin wire embedded in a bronze matrix. There's a photograph of what one of the actual magnet part of the NMR looks like, and what I've shown here is a sort of lines of force of that are generated by that magnet. What happens with this superconducting electromagnet is that a homogeneous field is created very in the center of that magnet, and it's in that field that the spins of the protein or other biological molecule whatever the molecule is, can align. The critical idea is that when spin 1/2 nuclei are placed inside that field, they align along the field, but there's two possible orientations with the field that could be parallel to or anti-parallel to the field, up or down. And we choose that up or down, the atoms choose that up or down spin distribution according to a Boltzmann distribution. It's beyond our range to go into that today, but suffice it to say that there's enough of a difference. We're not equally up and down, but there's enough of a difference for us to detect. There's a separation of those two spins, and that separation amounts to an energy. And that's the energy that we're interrogating when we hit the spins with that radio frequency radiation. So it just happens to be convenient that we can isolate those spins effectively, or identify those spins based on their response to radio frequency radiation. Now again, I don't want to spend too much time on this. Basically, we can have NMR is useful for nuclei that have one plus or minus 1/2 spins. There are others that are possible, but for now let's focus on those. And we can separate those amount to energy states, plus or minus 1/2, and we can separate those with a magnetic field, as I've already mentioned. That slight change in perfect homogeneity or equal distribution between up and down spins, again according to Boltzmann distribution, allows us to identify or visualize or record the responses of those spins to radio frequency pulses. The pulses themselves tend to redistribute the spins, and it's the change from that redistribution back to equilibrium that results in a release of RF energy, which we can detect with a radio antenna. Here's a list of biologically relevant nuclei. It's only worth pointing out these to you just because, of course, protons are something that we encounter in biological organisms. And you can see that there's a lot of them around, and they happen to be NMR sensitive. We'll see that carbon-12, which is very abundant, is not very NMR sensitive. Forget my phone. So instead, we have to enrich the protein with carbon 13, which is much less abundant, but we see that's our NMR active nucleus. Again, the same thing is true for nitrogen. The most abundant isotope of nitrogen is not NMR active, and so we enrich the protein, and I'll mention that briefly in a second, with an isotope of nitrogen that is sensitive to NMR frequencies. How do we enrich things? How do we enrich samples with with NMR sensitive isotopes? It's very simple. We'd create a medium for growing the organisms that are the bacteria, generally speaking, often that are growing our protein for us. And instead of just growing it in the standard chicken soup broth, what we will grow those bacteria in is a defined medium in which we provide as a carbon source sugar that's all labeled with carbon 13, or as a nitrogen source ammonium that's isotopically enriched for nitrogen 15, and no other food sources for the organism. So every carbon atom and every nitrogen atom that they incorporate comes from our labeled sugar and ammonium. So that's how we can introduce our labeled isotopes, and this in no significant way affects the structure of the molecule itself. Let's think about this, and this again is review for most of us from organic chemistry, but a key piece of information is that we can relate the chemical shift of different nuclei, to the identity of the nucleus for one thing, but also to within a kind of nucleus, say for carbons or nitrogens or protons, to exactly what kind of functional group that atom resides in. And we can see here's a range of chemical shift values, basically frequencies at which those nuclei respond to the NMR frequency radiation. And we can see that it's easy, for example, to identify an aromatic carbon, a carbon that's associated with an aromatic functional group, and to distinguish that from an alkyl carbon. Likewise, it's true for nitrogens. Amide nitrogens are easily distinguished from amino nitrogens, and that's interesting, for example, when we're considering peptide bond nitrogens versus primary amines at the ends of some side chains. Finally, as well, we can distinguish aryl from alkyl protons as well. So this is just giving us a general sense of our ability to distinguish a kind of nucleus based on where it resides, what kind of functional group it resides in. Well, again, here's more review for us, but it's worthwhile remembering this stuff before we talk about NMR spectra of proteins. So we've mentioned that each spin responds slightly differently to the applied external field, and then, but exactly what's happening is that we hit it with a radio frequency pulse and reorient the spin, but then when the pulse is relieved, the spin wants to reorient with respect to the magnetic field. So that realignment is effectively a ringing in the radio frequency range, and we can detect it with a radio antenna. But the intensity of the signal decreases as the spin comes back to equilibrium, and that's represented here in this is called a free induction decay diagram. Here's the intensity of the radio signal, and here's the time. And what we see is that we start out with this wave form that's oscillating, very intense at the beginning, but then the spins get back into equilibrium with the magnetic field and they die away. So it's a decay of the induction of that radio frequency radiation. Interestingly, if we have multiple spins, then we have a complicated waveform, and that's what we see here, a complicated waveform of overlapping spins. Sometimes they're canceling each other out, sometimes they're enhancing each other, and you can imagine in the case of a protein when we might have thousands of proton spins with their own individual frequency, we might have a very complicated waveform that we have to interpret. How do we get from this waveform, this time-dependent information, to frequency-dependent information? And that's using a mathematical trick called the Fourier transform, which again we won't go into, but all you need to remember is that the Fourier transform allows us to go from this time-dependent information to frequencies. So now we can transform that free induction decay to a spectrum, and here we see the frequencies with which each spin is resonating, perhaps, and now we can get something that's more recognizable as a spectrum. For proteins, it's very interesting. There's a variety of experiments that we can use to identify the atoms within proteins and assign a particular resonance to a particular atom in the protein. But let's keep it simple for now and say that we can detect through bond coupling between nuclei that are responding to our NMR frequency radiation. In this case, this is called a single quantum coherence fingerprint. We don't care about this so much. Just suffice it to say that we can create an NMR experiment in which we can look at the proton frequencies, but only those protons which are associated with nitrogens. And we remember which protons those are going to be. By and large, those are going to be the amide protons, right? Every amino acid in the chain is involved in a peptide bond, and every peptide bond has this proton-nitrogen pair. By screening the proton signals in this way, effectively screening out everything that isn't bound to nitrogen, we drastically simplify our NMR spectrum from potentially thousands of lines to only 100 or so, depending on the size of our protein. One, again, for each peptide bond. This is called a fingerprint because it's unique to each protein. Each individual amide nitrogen proton pair has a unique chemical environment, and so they'll have a unique set of chemical shifts. And so we can immediately tell that that this protein is folded, and B, that it's our protein of interest because it has this unique set of chemical shifts. Now, a big trick is assigning this spot to a particular amide, and that's easily done as well. And this is called sequential assignments, and it also uses through bond coupling. That is to say, this spin affects a spin a few bonds away. And we don't need to go into the details of those experiments. Suffice it to say that there are many, and what one can do is assign every resonance in an NMR spectrum to a particular atom in a protein. So in this way, and I think you can see that this is a fundamentally different way of approaching the structure determination problem than X-ray crystallography. And it's complicated, as is X-ray crystallography, but complicated in a different way. And it's more of a bookkeeping problem. Onward. Now, the problem with this method of molecular structure determination is that identification of each of those resonances as belonging to a particular atom doesn't tell us much about the spatial distribution of those atoms. And so there's more that we need to do than assigning resonances to atoms. And this is using a kind of NMR spectroscopy that's sensitive to through-space coupling. So one spin detects the presence of another spin or many other spins through space as opposed to through bonds. And this, you can imagine, can be used to calculate a three-dimensional structure. So this is a model building exercise effectively that amounts to creation of a list of atom-atom distances, and that list is a structural map. But it's not a map with a unique solution. And in fact, what we see in NMR structures is the creation of a family of possible solutions, and sometimes this is referred to as a blurrogram. And we have to decide on a way of selecting which sequences in that family are worth keeping, and typically it's a matter of deciding a cutoff for what deviates from the average solution to the problem. But it also gives you a reflection of where the dynamism in the structure might come from. And this is a place where crystallography actually falls down. So here, one must be careful to see that in this part of this particular structure, it looks like there's disorder, and you might think, well, our NMR spectrum actually tells us that there's a lot of disorder. What really the NMR data tell us is that there are a lot of ways to solve the model that meet the criteria set out by the data. So there's a lot of solutions to the problem for this element of the structure and for this element of the structure. In other cases, it's very, very tight, and there's very few ways to get the NMR spectra from a real structure. So that's a powerful way of interpreting NMR data. A few more slides on NMR. Let's see. What does an NMR structural solution actually look like in terms of input? Well, we have to develop a series of constraints. And first of all, I mentioned that we have to assign every resonance in the spectrum to an atom. Ideally, we assign all the protons and all the nitrogens and all the carbon resonances to a particular atom. And then we can use some other experiments that we haven't discussed to look at dihedral angles. And this is another through bond coupling kind of problem. We can use various techniques which again we won't discuss, to assign secondary structures. The one that I just discussed was it's called a NOE, or nuclear Overhauser effect, interatomic distances. This again is through space coupling, and even that method isn't terribly precise. We generally tend to decide only if atoms are near each other in space, close to each other in space, or far away in space. And again, that structure, that information allows us to create a model that satisfies all of these data, all of these constraints. So looking at a particular problem, a particular solution, I've shown you in the previous slide the structure, NMR structure, derived for alpha-conotoxin. We don't really care what this protein is, but let's just say that, yes, they assigned all the sequences. They were able to do some experiments to give them 18 backbone and 9 side chain dihedral angles, not very many when you consider the size of this protein. And then in terms of, they didn't use these other methods in this structure solution, they used these NOEs. Some were within a particular residue, but for those NOEs or those interactions that were between different amino acids, we see that it's only a couple hundred or a few hundred constraints that we give our model building program that allows us to come up with our structure. And so again, as in crystallography, there's some certain parameters that we build into things that are particularly important in NMR in terms of model building. We teach our computer how long a bond should be, how strong a bond should be, what difference between covalent and non-covalent interactions, what are possible or versus ideal torsional angles, and then we feed it our experimental constraints. And then the computer uses an algorithm to fit the data to these constraints. And again, we don't need to go through all of those, but it involves, again, a generation of the family of structures that fit our data, and then the assessment of those violations. So does our solution have bonds that are too long, populate part of phi size space that's not allowed, etc., etc. And then we select among those solutions for those that deviate from one another the least, and we call that our average structure. Here, this blurgram is made up of 20 structures. The authors published 20 different structures in their PDB entry, and these structures have an RMSD of 0.75 angstroms, and that's for all atoms. So what is an RMSD? This is an interesting term. Root mean squared deviation. Basically, if we calculate one average structure, we can say how far away from that structure any individual atom is. And for all the atoms in the molecule, we'll say it's 0.75. But if we only consider backbone atoms, it's much tighter. So that's an interesting detail as well. Let's move on to we're almost done here. Let's just say what are the limitations and advantages of these two molecular structure determination methods? Well, for NMR, solubility is an issue. We have to have proteins that are soluble up to 3 millimolar or so. They also have to be stable and folded. If they're not stable and folded, then we can't get unique chemical shift information, and we can't determine the structure. Likewise, if there's structural heterogeneity, this is related to the folding and stability problem. If the protein adopts multiple conformations, then that leads to a very confusing NMR spectrum, and we can't really interpret it very well. And finally, most of the time we're restricted in traditional NMR experiments to monitoring the structures or determining the structures of relatively small proteins. However, if your protein's not crystallizable, that's okay as long as there's not aggregation and it remains soluble. And oftentimes NMR is a perfectly good tool for proteins that otherwise wouldn't work in crystallography, because no matter what concentration we get them to, they never crystallize. What does that tell us? That tells us they remain in solution, right? It allows us to interrogate conformational dynamics sometimes, so we can look at structural changes, and we can also look at intermolecular interactions, and we'll see examples of these as the semester goes along. But we can imagine that our NMR spectra of our labeled protein might change when we present the protein with a binding partner that isn't labeled. So we can use NMR to ask questions about the behavior of proteins that are often more difficult to address by X-ray crystallography. Okay, that brings us to the end of our molecular structure determination series, and we'll begin next week with more protein function. See you there.